All right, let's do a couple examples of vector field problems. So the first one says match the vector field F on R3 with the correct plot, and then they give you the vector field. It looks like F of x, y, z is 2i plus 3j plus 4k. So another way to write that would be 2, 3, 4. All right. So it turns out this vector field is really just a constant, right? So at every single point, they want you to create a vector, and that vector should be, over 2, over 3, up 4, right? So it kind of goes from a point, it's going to go in that direction. But then every single point in space, they're all going to be going in that direction. So what we really should be looking for is something where it kind of has that look to it. So this one, it looks almost like a radial vector field, like everything's kind of pointing out from the origin. This one, everything's kind of pointing up, but some over this way, some over that way. This one, they're kind of pointing down, but some over, some down. This one, they all appear to be pointing in the same direction. And let's see, here's 0, and here's 0, and here's 0. So 0, 0, 0 is kind of right in the center. And so this should be positive that way. And they do kind of all be, yeah, they look like they're moving that way. So that should be that one. So that's kind of the way you want to think about these problems. Look at what do they give you, and then can you see how to pick out which one it is. Okay, and then a second example problem here. So in this one, they say find the gradient vector field of F. Oh, okay. So they give you F here. That's just some multivariable function. Here it is. And then they say find the gradient. So the gradient of a vector, given a function, f of x, y, z, we can compute the gradient of that function. And the gradient is going to be a vector field with 1, 2, 3 components in it. And this is going to be the x derivative, this is going to be the y derivative, and this is going to be the z derivative of that function f of x, y, z. So if f is the function 7 times the square root of x squared plus y squared plus z squared, then the x derivative would be 7 times 1/2 times x squared plus y squared plus z squared to the negative 1/2 times the derivative of the inside with respect to x, which is 2x. The y derivative will be 7 times 1/2 x squared plus y squared plus z squared to the negative 1/2 times 2y. And the z derivative will be 7 times 1/2 x squared plus y squared plus z squared to the negative 1/2 times 2z. And then the gradient will then be, we could do a little bit of canceling here if we wanted to, 1/2 with the 2, 1/2 with the 2, 1/2 with the 2. We're going to get, okay, so 7x, so I'm just going to write 7x over, I can even write that with a square root, x squared plus y squared plus z squared, 7y over the square root of x squared plus y squared plus z squared, and then 7z over the square root of x squared plus y squared plus z squared. All right, so if you have a function like this, and you take the gradient, now we've got a vector field. So now you might wonder, what kind of vector field do we have here? I think it's actually a radial field because it's basically x, y, z, well, 7 x, y, z. It's shrunk it's being scaled here, but they're all being scaled by the radius. So yeah, that will end up being a radial vector field, which is kind of an interesting little problem. All right, so there's a couple examples of vector fields. How do you think about what they look like? How do you take gradients? And if you can do those, you should be able to do any problems with a vector field.